Okie doke. As we march through Thomas's calculus, chapter 8 is a whole chapter about here's an integral, how do I evaluate that integral? And we've talked about integration by parts, and we've talked about integrals where the integrand is trig functions to powers. We've talked about how to do integration by trig substitution. In this screencast, we're going to do some pre-calculus that ends up being helpful to us in calculus. There's not a lot of calculus today, and the calculus is not very difficult, but the calculus is going to get us out of some trouble. So let's pretend, we'll pull out the little red trolley and pretend, let's pretend that I wanted to integrate this. Oh, sorry, this. What techniques do we have at our disposal? Well, sometimes we think about U substitution, and U substitution is not a bad idea here because the powers in numerator and denominator are 1 apart, but the derivative of the denominator is 3x squared minus 8x, and that doesn't jive with what's happening up here. So that's not looking good. Integration by parts is useless. Trig sub, oh gosh, trig sub would be a disaster. So what if I were able to tell you that this integral is the same as this integral? You would say, I'm so glad that you stalled for time by factoring, but I really don't know what to do with that. Okay, well, I agree. I agree. Well, what if I told you that this integral is the same as this integral? What if I told you that those were the same? Oh, now we're getting somewhere because I can do this and I can do this and I can do that. In fact, none of them are terribly difficult. Oh, sorry. So your legitimate question might be, how do I go from here to there? And the method on how to go from here to there is called partial fraction decomposition. And the reason it is called partial fraction decomposition is because it takes a fraction that has 1, 2, 3 factors in its denominator and turns it into 1, 2, 3 fractions where those factors are the denominators. How do we do that? Well, consider the following. Bill Nye the Science Guy. 1 over x squared minus 7x plus 10 dx. How do we do this? Well, what we'd really like to do is we'd really like to turn this into the sum of two other fractions whose denominators are the factors of x squared minus 7x plus 10. I mean, clearly, x squared minus 7x plus 10 factors into x minus 2 and x minus 5. So there is pre-calculus mathematics that we can do that turns the fraction on the left into the sum of fractions on the right. One other point to make here in this lesson that is somewhat significant, and then everything after that is easy peasy. This is a proper fraction. The degree of the numerator is less than the degree of the denominator. The degree of the denominator is 2, that's the highest power of x. So the numerator cannot have any power 2 or higher. This is a proper fraction. Therefore, this must be a proper fraction, and this must be a proper fraction. Well, the powers here are 1, x to the 1. So the numerator cannot have an x to the 1 or any higher power. And if you can't have a power of x to the 1, you have to be some constant. You have to be some constant. And so really, if we knew what a and b were, we'd be done. Well, we do, because I know how to add fractions whose denominators are different. If I'm adding fractions whose denominators are different, I multiply everybody by the other denominator. And so it turns out that a times x minus 5 plus b times x minus 2 is 1. So if I know what a and b are, I'm done. I'm going to scroll down for a moment. We'll go back up when we need to. Thought. This holds for all values of x, and so specifically it holds for x equals 5. Why would I let x be 5? What advantage do I have if I let x be 5? Oh, that's right, you do. B is a third. Can you guess what other x value we are going to use? Yes, scream it at your YouTube screen. A times, right? Oh, sorry. A is minus a third. So why does that matter? Well, because this integral is the same as the integral of a over x minus 2 plus b over x minus 5 dx. And we know what a is, and we know what b is. And we know how to do this integral. It's not hard. This is a natural log. And we know how to do this integral. It's a natural log. Don't forget plus a constant. There it is. Now, side note, in the back of the book, you're going to see it written like this, because that saves space, and I'm going to leave it up to you and your properties of logs to know why those two things are the same. Okay? Okay. I'm going to do this one more time. I'm going to do it a little bit faster, and you're going to be able to follow all the steps. So our thought is we want to turn this into the sum of three fractions whose denominators are the denominators. And each of these is a proper fraction, so that's a number, that's a number, that's a number. So if we were to combine these fractions, we'd multiply everybody by every other denominator, and we'd get a times the other two denominators plus b times the other two denominators plus c times the other two denominators has to equal this thing. And then we're going to try three values of x. I would try x equals 1, and I would try x equals 4, and I would try x equals negative 2. You may even want to take a moment and do those substitutions. You get three easy equations to solve. I'll wait. Hit the pause button. Hopefully you figured out that a is negative 1/6 and b is 1 and c is 1/6. And the upshot of that is that I can do these three integrals. I don't know how to do this, but I know how to do this, I know how to do this, I know how to do that. In fact, all of them are natural log. This is a natural log. Don't forget the absolute value bars. This is a natural log with a u sub in its head. And this is a natural log. Never forget to add the constant c. Okay. You might well pause, not that we're done, but you might pause to check for understanding. You might try to integrate 2x minus 1 over x squared minus 5x plus 6. And you may try to integrate negative 4x plus 6 over x minus 1 times x minus 2 times x minus 3 dx. You may take a moment and do that. We can talk about that when we gather in class. Not a big deal. A couple of things we should talk about beyond those. This process holds for proper fractions. Proper fractions. So what happens with this? What happens with that? Well, I'll tell you what happens with that. Long division happens with that. We literally go back to 4th grade and divide x squared minus 4 into x cubed plus 1. We literally go back to 4th grade and long divide. Now, you may have to find some Khan Academy video on how to long divide polynomials. I'll give you the upshot. How many times does x squared go into x cubed? Well, that depends. What's that? Right? Okay. So x squared goes into x cubed x times. And then when you were in 3rd grade, you multiplied, and subtracted. And if you subtract, you get 4x plus 1. Well, this degree is less than that degree, and so we're done. This integral is the same as the integral of x plus remainder over divisor. These two quantities are the same. Now, I know what you're saying to yourself. You're saying, self, I know how to find this integral. This is easy. This looks difficult, but it's a proper fraction. And since it's a proper fraction, I should be able to break it up into 2 fractions, one of whose denominators is x minus 2, and the other of whose denominators is x plus 2, and this should be a number, and that should be a number, and I should be able to pull this off. And I agree with you. You should be able to pull this off. In fact, on scrap paper somewhere, you should be able to say a over x minus 2 plus b over x plus 2 should equal this fraction, and you should run a process very similar to the one we've used to figure out that this is 9/4 and this is 7/4. And once you do that, it's easy. I know how to find that antiderivative. The 9/4 is ugly, but it doesn't change how we do the thing. And the 7/4 is not that attractive, but it still doesn't change how we do the thing. You put a big box around it. So again, the tricky piece here is recognizing this is not a proper fraction. We must make a proper fraction out of it, but this process is the same one we've been working on. The other thing to think about is, what do you do with this scenario? 18 over x plus 3 times x squared plus 9. What do you do with that? Because I know what you're thinking. You're thinking, this is already factored, so I should be able to come up with two proper fractions whose denominators are this thing and this thing. I should be able to come up with two proper fractions whose denominators are those things. Right. This factor has degree 1, so this must be a constant. This factor has degree 2, so this numerator could have degree 1 or it could have degree 0. It could have degree 1 or it could have degree 0. We basically take all the powers that are less than this one and string them together. That's basically what we did here. Take all the powers that are less than this one and string them together. So, same as before. Everybody gets multiplied by everybody else. Right? Compare the numerators. This times this times this, that's the other numerator. And then there are some things we get to choose. What x's might we choose? Well, I might choose x equals -3 because that's going to make my life really, really easy. This factor drops out. If x is -3, that's 18a equal to 18. That's a nice easy a. You're like, this course is not an easy A. I know, falsetto boy, I know. Another obvious choice might be to pick x equals 0, because if x equals 0, the b drops out. If x equals 0, this is 9 times a, which we already know to be 1. X equals 0, this is c times 3 equal to 18. And that tells us what c is. And then we can pick any number in the world to tell us what b is. I'm going to choose 1 because that's going to give me a 1b. So this means 10a, which we already know to be 1, plus b plus 3 times 4 has to be 18. And that tells us that b is -1. So this integral is the same as this integral. This integral is this integral is the same as this integral. So what happens from here? This we know, this we don't. Even if we split it up, this we know. This is a u sub. U is the denominator. The du is 2x dx. So you get a 2 and the 1/2 to compensate. This is a trig sub problem. This you may want to work out as a trig sub problem. Radical x squared plus 9 on the hypotenuse of a right triangle, x and 3 the other sides. When it's all said and done, this one's straightforward. The second one less so. And the third one turns out to be that. Okay? Not a lot of calculus in today's lesson. A lot of pre-calculus, a lot of pre-calculus that helps us to do the calculus a little bit better. I look forward to taking all of your questions when we gather, which hopefully is very soon.